Hello everyone. Thank you all for listening to my presentation today. My name is Ayako Mizushima from the University of Tokyo in Japan. Today I'd like to talk about problem of silicon dioxide membrane and treatment which we tried. Membrane is one of the essential structures of MEMS and optical devices. As an example, this is direct fine patterning by using thin silicon nitride membrane shadow mask. These metal dots are 300 nanometer size. These were formed vacuum evaporated directly through perforated silicon nitride. And the other example is an application for optical device. By using gamma aluminum oxide membrane, generation of vacuum ultraviolet was measured. To date, silicon dioxide has been believed to be inappropriate material to produce flat membrane because of compressive stress that is common for thermally grown silicon dioxide. However, silicon dioxide membrane has been required because of its good hydrophilic property or spectral characteristics and so on. Our past experience during MEMS microactuator fabrication also confirmed that thermal silicon dioxide membrane wrinkles as soon as it is released to freestanding. One of the only methods to make freestanding wrinkle-less thermal silicon dioxide film was to structurally enforce them, such as rolling, to produce hollow pipe structure. These are images of compressive stress and SiO2 tensile stress on silicon dioxide. Membrane of compressive stress silicon dioxide wrinkles when it's freestanding. Membrane SiO2 tensile stress silicon dioxide is presumed to be without wrinkling. CVD silicon dioxide was known to be capable of producing tensile stress. The stress can be controlled by deposition parameter optimization. So this time, we prepared very low tensile stress CVD silicon dioxide. But we don't have CVD equipment, so we got them with the cooperation of a foundry company. And then we fabricated membrane. This shows the process flow which we done for membrane fabrication. First, we had mirror polishing on the back side of the chip by CMP. And then we coated resist on the top side of the chip for protect the silicon dioxide surface. On the back side, we made a thick resist pattern. The resist thickness was 7 micrometer. And that was formed by photolithography using a direct laser writer. The next was through the wafer etching, deep RIE. Actually, such a chip etching, we attach the chip to 4 inches dummy wafer and fill the gap between the chip and wafers with silicon oil to avoid heating up during high power etching. As a side note, the dummy wafer was silicon wafer but coated with spattered aluminum to prevent from etching. We stopped etching as soon as a part of the membrane has been exposed. And after resist removal by solvent, the chip was diced into smaller pieces. This is a membrane which we produced first. These are top view and the bottom view by microscope observation. The exposed area was 700 micrometer. It's a large aperture size. And the size of exposed area was depends on pieces from about 400 to 700 micrometer squares. This membrane was not wrinkling. We could make wrinkle-free silicon dioxide membrane by using stress-controlled CVD silicon dioxide. But this might be a beginner's luck, because our second result was different. This membrane was fabricated one after a month. It was wrinkling. The chip was obtained from the same method as the first trial. The wrinkling occurred regardless finishing treatment, both all dry process and wet last process. It means not only deep RE, finished with TMH wet etching. Then we noticed from a research paper that CVD silicon dioxide does absorb humidity and thereby elongating the membrane. So we put the chip into annealing. Annealing temperature was 800 centigrades in nitrogen gas for 30 minutes. These are observation results by laser confocal microscope before annealing and after annealing. The annealing did work for this wrinkling membrane back to flat. We try to estimate the membrane elongation and inducing stress. Simple structural mechanics, the membrane elongation can be estimated. This is an approximate calculation, the bowing shape to triangle. And such elongation induces 122 megapascal of compressive stress to the silicon dioxide thin film of the initial length, which is good accordance with time-dependent relaxation of tensile stress. To confirm dependence of wrinkle appearance of annealing temperature, we put one chip into 400 centigrades annealing. After annealing, the chip was kept in our clean room, which controlled 23 centigrades and 20 to 40% relative humidity. Indeed, the chip became flat after annealing. However, wrinkled back in 2 days. This graph indicates profile of the membrane wrinkling before annealing. It became flat after annealing. However, deflection had appeared in the next day, and it got larger and larger, day by day. The deflection was even larger in 2 weeks than that of before annealing. This graph shows the maximum deflection depth changes according to annealing temperature. For the first 20 days, 500 centigrade annealing membrane seemed to be flat. So we considered around 500 as a critical temperature and fabricated 6 additional chips and the various annealing temperature between 400 to 500. The measurement told that the sample annealed 450, wrinkled in a couple of days. The sample between 450 and 500 also wrinkled but slower change, and 500 also began to deform after 1 month. Sometimes the maximum deflection value seems skewed because wrinkles have irregular shape. On the contrary, membrane annealed at 600 and 800 have been stable and flat for more than 3 months. These experiments suggest that the border is between 500 and 600. And to interpret these results, below 500 annealing work as a kind of dehydration bake. Membrane turned to flat once but became wrinkled again with humidity absorption. And above 600 centigrade annealing work for characteristic change. To be more specific, hydroxyl group containing in silicon dioxide structure is considered to be relevant with humidity absorption. This hypothesis is to be verified. Moreover, we also confirmed effect of pre-annealing. That means annealing, and then we did membrane fabrication with annealed chips. Annealing conditions were temperatures were 400, 600, and 800 centigrades in nitrogen gas for 30 minutes. After membrane fabrication, the chip had been kept in the clean room at the same condition as post-annealing test. This graph shows the change of pre-annealed membrane deflection. As same as post-annealing, 600 and 800 annealed membrane have been stable without wrinkle for 3 months. Considering the property of membrane changing, those results seemed reasonable. And even now, we are continuing the observation once a week for both post-annealing and pre-annealing samples. In conclusions, we have demonstrated wrinkle-free silicon dioxide membrane. Using stress-controlled silicon dioxide by CVD, simple nitrogen annealing was sufficient to recover flat membrane. We have assessed annealing temperature dependence of wrinkling. Annealing above 400 centigrades was effective to make membrane flat. But annealing below 500 centigrades made membranes wrinkled again. Annealing above 600 centigrades, membranes stayed flat for at least 3 months. Humidity absorption is suspected for the cause of wrinkling. For future works, we would like to analyze characteristic change of silicon dioxide for before and after annealing and verify the hypothesis. I'd like to close my presentation. Thank you so much for taking the time to join today.